Hello, everyone, and welcome to Algebra 2. This is section 9.2, Angles and Radian Measure. So in a coordinate plane, an angle can be formed by fixing one ray, called an initial side, and rotating the other ray, called the terminal side, about the vertex. So that point right there is going to be called the vertex. If the angle is in standard position, then the vertex is at the origin and the initial side lies on the positive x-axis. So then positive angles have a counterclockwise rotation, and negative angles will have a counterclockwise rotation. So we'll do a few examples here to help you see what I mean. This is 0 degrees, just in case you didn't remember this from another class, 180 degrees over here, and 270. A circle is a total of 360 degrees. So if I want to draw a 240-degree angle, I start on the positive x-axis, and I go around until I reach 240. Now, you don't have to know exactly where that is, but as long as you get it in the right basic area, that's all I'm looking for. Now, 175 is really close to 180. So you should draw it a little bit more like that than just somewhere in quadrant 2. The next one is negative, which means I'm still going to start at the positive x-axis, but I'm going to go counterclockwise. And it should be right down the middle because it's half of the 90. So this angle right here is minus 45 degrees. You'll notice on the last one, I just realized I didn't draw the x-axis part of the angle. That's pretty common. Because that's always the beginning of the angle, when people want to draw 175, they really just need to draw that one point right there, 175. So again, negative 300 is going to go backwards. And since all the way around would be 360, I don't want to quite go all the way around. But this right here would be my minus 300 degrees. And it's just 60 short of going all the way around. Now, it is possible to have an angle that is larger than 360 degrees. But because the circle just keeps going around and around and around, they are considered coterminal with other angles that are the same. So maybe you've done a 45-degree angle, but maybe you actually went all the way around once and then stopped at 45, and it looks exactly the same. So what we're going to do is we're going to find one positive angle and one negative angle that are coterminal, I mean they end in the exact same spot with the angles. So let's draw it. Negative 45 degrees is right here. But if I went around another 360, that's a full circle. I would land in the exact same spot. So negative 45 minus another 360 is going to give me negative 405. I don't actually want a negative 405-degree angle, but sometimes you'll get one, and I want you to know that it's the same as negative 45. Or somebody might get to this spot by going counterclockwise, as positive angles do. And that distance would be 315. And you can get that from adding 360. In other words, if you're right here and you think about it as going all the way around, adding 360 in the counterclockwise direction, you'll end up with 315. So this angle, 315, and negative 405 and negative 45 are called coterminal. They all look exactly like this. If you didn't have the little arrow showing you which way you got there, they would all just look like this green ray right there. All right, so you could try the next two on your own. So 395 is already bigger than 360. So this is a good example of one that we don't want 395. So I can take the 395, which maybe I can't really envision because my circle only goes up to 360. but I can go back around once. So I subtract 360, and then I get 35. And then it's like, oh, 35, I know where that is. This is 35. So this angle is both 35 degrees and 395 degrees. Now they do ask for a negative angle also. So I subtracted 360 to get to 35. I can subtract 360 again. So I'm going to go around the circle again, clockwise, and I will get negative 325. So while I hope that these explanations have helped you understand the concept of coterminal angles, if you don't quite get it, then the key is just to add 360 or subtract 360, and that's how you get a coterminal angle. So even if I didn't draw it, even if I didn't understand it, if you took 80 and added 360, and then you took 80 and subtracted 360, this is going once around the circle positive and then once around the circle negative, you would get a coterminal angle. This one would be 440 degrees, and this one would be negative 280 degrees. 80 degrees is right about there, maybe even steeper, because of course the right angle is 90. So the point is that 440 means somebody has gone 360 around plus 80. They went a full circle, and then they went 80 more, but because the full circle got them right back where they started, it just looks like 80. So 80 and 440 look the same. Or if somebody's at 80 and they go clockwise 360, they're also going to end up at the exact same spot, but this time we would call it negative 280. Okay, there are 3 more to try on your own. But of course, I am going to do them for you. So I always like to draw just because I think you should be practicing where these angles are. So remember that this is 180 and this is 270. So 230 must be somewhere in here. How do I find a coterminal angle with that? Well, if I subtract 360, then I'm right here, and I'm going to go backwards, and that gives me negative 130. So if somebody started at the x-axis and went this way, they could get to the exact same angle by going clockwise 130 degrees. But they could go clockwise around the circle, so they could add another 360, and that would be 590 degrees. So if somebody ever said to you, where is 590 degrees? You would say, well, that's bigger than 360. So right away, they've gone around the circle once, and then they've gone another 230 degrees. Still 2 more if you're still just letting me do them. 740. This one's the opposite of what we just did. This one's already bigger than 360. So I'm going to, when I subtract 360, I'm just hoping that puts me back in the unit circle. So 740 minus 360 is still 380. It's still bigger than a whole circle. But if you want to see what it looks like, you can subtract 360 again. So this is coterminal, but so is 20 degrees. All coterminal with 740. If I drew any one of these, they would look exactly the same. They would look like this. But they did ask you to find a positive one and a negative one, and I've only found 2 positive ones. So I'm actually going to subtract 360 one more time, and that gives me negative 340, and now I have a negative 1. All these 4 boxed answers look exactly the same. They look like that. Last one, negative 135. So I can picture this. This is 180 over here. And so if I go negative 135, I'm going this way, counter or clockwise for negative. But if I want to know what that angle is that's coterminal to it, I can just add 360 degrees, and I get 225. So 225 in this direction would give me the same thing. Put it exactly at that spot. If I want another negative one, I can just subtract 360. And I get negative 495 degrees. And these are called coterminal. Now, for higher level mathematics, you will need to become familiar with another unit commonly used in the measurement of angles, and it's called radian measure. It's a little tricky at first, but in the end, most people actually end up liking radian measure better than degrees, and in calculus, we don't use degrees at all. We solely use radian measure, so it is something you're going to want to pay attention to and understand. So to help you understand it just a little bit, think about the circumference of a circle. The circumference of a circle means the distance all the way around that circle. But what could change the circumference of a circle? The size of the circle. So if I made the circle smaller, a smaller radius, then the circumference is smaller. If I made a really large circle with a really big radius, that radius is going to make a bigger circumference. So you might remember that the formula for circumference is 2 pi r. So the 2 and the pi are constants, only the r changes. What does the 2 pi represent? The way around the circle. So if this is your radius and you go around the circle to get the circumference, or if this is your radius, it's tiny, and you go around the circle, the way around the circle is 2 pi. So that's what our new measurement is going to be. All the way around is going to be 2 pi. You guys are used to 2 pi being 360 degrees. Now you have to think of all the way around the circle as 2 pi, which means if you only go halfway around the circle, you're at pi, which you formerly knew as 180 degrees. If you only go a quarter of the circle, then you're only going half of a pi. Now, we don't actually write half pi. It's common to write it as pi halves. So pi halves is going to be your new 90 degrees. So somebody actually filled in this circle for you. So it's all written down here. You definitely want to transfer this to your appendix. And when you first look at it, you might be thinking, it's a lot to know. I am going to just show you something that might make it a little bit easier for you to learn the unit circle. And that is, in addition to these lines right here, they kind of had a little gap there, right? So if I fill those in, the circle is actually broken down into twelfths. So this is 1/12 of pi, which we're going to call pi twelfths. And this is 2/12 of pi, which reduces to 1/6. This is 3/12, which reduces to 1/4. This one is 4/12, which reduces to 1/3. This one that they don't show you is 5/12. We really don't use the twelfths very much. So they didn't even put them on the circle. And this is 5/12 and then 6/12. So if you kept doing that, 7/12, 8/12, 9/12, 11/12, or 10/12, 12, 11/12, 12/12, then you would get all the way around the circle until you get to 24/12, which would be 2 pi, 24/12. So do you have to think of it in twelfths? No, but I'm only showing you that because for some people that helps their mind grasp this weird pi 6, pi 4s, pi thirds, pi halves. It's actually just all twelfths that's been reduced. Another thing that helps me personally start to learn the unit circle is thinking about how all the pi 6 go together. So there's pi 6, and 5 pi 6 makes the exact same angle from the x-axis. See that angle and that angle? They're the same. But this one is just 1/6 starting out, where this one is almost at pi, right? So it's 5/6. It's the same measure, but it's 1/6 short of being all the way around, so it's 5/6. And then this one, doesn't that one also look like it's making the exact same angle? It's 7/6. It's one more than a whole. And this one is 11/6. So all the 6s are in the same location in the sense that they make the exact same angle with the x-axis. But this one is one short. Remember, 12 pi 6 would be right here at 2 pi. So this is one short of 2 pi. So it's 11/6. And then I could make that same argument for every single one of these. So here's pi fourths, 1/4, 2/4, 3/4, 4/4. Or, like I said, the way I think about it is that this one is 1/4 away from the x-axis, and then this one is missing a fourth. See how it's 3/4? It's almost at a pi, but it's only 3/4 of the way. Where this one has reached pi plus a fourth. So it's 5/4, and then 7 pi fourths. And you could think about that for all of them if you wanted to. Okay, final way. I know I'm harping on this, but you're going to have to memorize this unit circle. So I'm just trying to give you ideas for how to do that. So the other way I think about it is that all of these are plane, just pi 6, pi 4s, pi thirds. In this quadrant, which is quadrant 2, these are always one less. So it's 2/3, 3/4, 5/6. See how the numerator is always one less than the denominator? Where in quadrant 3, because it's more than a pi, it's one more than a pi, 7 pi 6, 5 pi fourths, and 4 pi thirds. It's always one greater than the denominator. That helps me a lot. And finally, in quadrant 4, this is a little harder to know, but you could just think to yourself, well, it's a lot bigger. But the actual thing is it's twice 2 minus 1. So if you take 6, multiply by 2, and then subtract 1, you'll get 11. 4 times 2 minus 1 is 7. 3 times 2 is 6, minus 1 is 5. So it's times 2 minus 1. Of course, there's lots of angles that are not on our unit circle. So I see 210 can be converted to 7 pi 6, but what about 215? That's not on my unit circle. So for anything else, you can easily convert from degrees to radians or radians to degrees using this fact. We call this a conversion factor. You've been using conversion factors for years and you just maybe didn't call them that or didn't know you were doing it. So for example, if I had 5 feet and I asked you to convert that to inches, you might just sit there and say, well, we'll just multiply by 12. But the actual conversion, that's true, but the actual conversion factor is you'd put the feet on the bottom because you want them to cancel and you want your answer to end up with inches. So you'd say there are 12 inches in one, I know I wrote feet, but 1 foot. So how do you convert this? Now you can cancel your feet and you have 5 times 12 is 60 inches. That's called a conversion factor. We're going to do that to convert from degrees to radians, and we'll use this conversion factor. So I have 120 degrees. I want to convert it to radians. So I put degrees on the bottom because I want that to cancel, and I put radians on the top. So unfortunately, radian doesn't have a little unit. There's no little degree symbol, or there's no symbol. It's just radians. And now I can cancel the degrees with the degrees cancels, and I get 120 pi over 180, which of course you don't want to leave it like that. You want to reduce, and that reduces to 2 pi dividing by 60 over 3. Now this one is on the unit circle. So anything that's on the unit circle, I would love for you to just memorize. But on the outside chance you forget one, you can use this conversion. The next one is already in radians, so I can tell by the pi mostly, but also by the lack of a degree symbol. So this time I'm going to multiply by 180 on the top because I'm trying to get there to be degrees and I want to get rid of the radians. And sure enough, the radians cancel, even though there's no actual unit to cancel, and I get negative 180 over 12, which is negative 15 degrees. 135 is in degrees. So I want the degrees to cancel, so I put it on the bottom. 180 degrees is to pi. That's my conversion factor. So now don't actually multiply pi in your calculator. Leave pi in your answer. And then you can reduce that. And it reduces to 3 pi over 4. Again, this one is on our unit circle, so you could just memorize that one. The next one's on our unit circle too, but as we sit here and practice this, again, I'm trying to get the pi to cancel, and I want to have degrees in my answer. So that's my conversion factor. I cancel the pi's. I do 5 times 180 divided by 4, and I get 225 degrees. And the last one, I have negative 40 degrees. So I want the degrees to cancel. So I put the degrees on the bottom of my conversion factor, and I put the pi on the top. I want to leave pi in my answer, and you're pretty much just reducing. So you're thinking 4 and 18 reduces to 2 and 9. Don't forget your negative. And that's how you convert. But the more of these that you just know by heart, the better. I would really only use this for an angle that you don't know. That's not on the chart, like negative pi over 12. So there are lots of word problem applications for this concept. The first is how to find the area of a sector. A sector is a region of a circle that is bounded by 2 radii and an arc of a circle. The central angle of the sector is the angle formed by the 2 radians. So we call this the central angle. Here's one radius, here's the other radius, and then this is the arc length. So if you encapsulate that whole thing, you get this. That's the sector. So there's 2 parts of the sector that we have formulas for. The first is the length of this curved arc here. And that formula is S is equal to r theta. And then the area of the whole thing, which is 1/2 r squared theta. Make sure you put those 2 formulas in your appendix. But most importantly, you're going to need to like star, circle, bold, whatever it takes. Theta must be in radians. I cannot tell you how hard I work to make this a really big deal every year. And every year, somebody in the class misses it. You're going to get the problem wrong if it's not in radians. And I won't give you partial credit because I am literally giving you as much warning about this as I can. So this says that a softball field forms a sector with the dimensions shown. Find the length of the outfield fence. So there's a fence going along here. So for the fence, we want the arc length formula. S is equal to r theta. And then we want the area of the field. And to get the area of the field, we're going to use area is equal to 1/2 r squared theta. So my radius is 200 and my theta is 90. But it must be in radians. So this is going to be pi halves. The formula only works in radian measure. As you get in higher level math, lots of things will only work in radian measure. So even though you generally are going to leave pi in your angles for radian measure, if you're actually doing a word problem, then that doesn't make sense. Nobody would sit there and say, oh, I have a fence that's 100 pi units long. It doesn't even make any sense. So go ahead and actually multiply that out. And of course, you'll get, because pi is about 3.14, you do have to know the next few digits. So 314.159 feet is the fence length. And then for the area of the field, it's going to be 1/2 200 squared, and again, pi halves. And you can just type that into your calculator. There's a pi button. Don't use 3.14. Actually use the pi button, which is above the caret key. And you'll get 31,415.927 feet squared. Make sure you have your unit. Okay, so make sure these 2 formulas are in your appendix, but most importantly, put whatever stars, exclamation points, whatever you need to remind yourself that it has to be in radian measure. A spiral staircase has 15 steps. Each step is a sector with a radius of 42 inches and a central angle of pi-8. So I would be terrible trying to draw this spiral staircase, but I can draw one stair on my spiral staircase. So there's my pole, and then, you know, they would keep going around, but they're also going up. Yeah, I have no shot. So I can tell you that this angle is pi-8, and each step has a radius of 42 inches, which is a double line. What is the length of the arc formed by the outer edge of each step? So for me, I always write the formula first. S is equal to r theta. And when you're getting your papers graded, that also lets me know that you had a plan, you knew what you were looking for. And then you just fill it in. 42, it's already. So this is really ironic. I make such a big deal about converting that sometimes when I give kids the answer, when I give the problem in radians, then they switch it to degrees because they're just so convinced they have to switch it. The point is not that you have to always switch it. The point is that it always has to be in radians. And this comes out to be 16.493 inches. Through what angle would you rotate by climbing the stairs? So when you're on this first step, you're going to rotate pi-8. But then on the next step, which is going to like pick up where that one left off, but it's going to be higher. And then the next one is going to be higher, but it's going to pick up where this one left off. So it's going to keep getting, I definitely can't draw this, but in other words, you're going to go pi-8 and then pi-8 and then pi-8 around and around and around, and you're going to do it 15 times. So 15 times pi-8, which, like I said, with an angle, you're actually welcome to leave it in that unit of measure. But if it helps you understand what it comes out to, for a little while, some people just, it's easier for them to think in degrees. So 337.5 degrees, but it was given in radians. You're allowed to leave it in radians. So you're going to cover the staircase with carpeting. How many square inches of carpeting would you need to cover the 15 steps? So 1 step area times 15. So remember that the formula for area is 1/2 r squared theta. So 1/2 42 squared. And again, this is already in radians, so we're all set. And then times 15. And that comes out to be 5,195.409 square inches. Next one. In the men's shot put event at the 2012 Summer Olympic Games, the length of the winning shot was 21.89 meters. A shot put must land within a sector having a central angle of 34.92 to be considered fair. So I don't know if you've ever seen a shot put sector, but the guy, when he stands here and he kind of spins around and then he throws it, sometimes he throws it and it lands out there. If it lands out there, then it's not considered good and he doesn't get credit for it. Okay. So, this, in this men's shot put event, the winning shot was 21.89. So it was way out here at 21.89. No matter where it was on here, that would be considered the radius. And then his angle is 34.92 degrees. The officials draw an arc across the fair landing area, marking the furthest throw. Find the length of the arc. So I always write down my formula first, and then I fill it in. 21.89. Ooh, but this is in degrees. This formula won't work in degrees. So I have to take a step back, and I have to convert it. 34.92. It's in degrees. So when I convert, I put my degrees on the bottom and my radian measure on top. So 34.92. Remember to use the pi button. Divided by 180 is 0.60946897. Now you're thinking, I thought we could round to the nearest thousandth. You can, but not yet, because you're about to multiply by something. So you can't round mid-problem. But you can just leave that in your calculator and then hit times 21.89. And so you don't have to worry about rounding at all. And then you get a final answer. Now you can round. So it's 13.341. And what are we in? Meters. That's going to be this length of this arc right here. But now the question is, what is the area of the sector? The area is 1/2 r squared theta. So interestingly, instead of just hitting times answer, you could have stored that value and then you could use it again in its entirety without having to type it in. So 1/2 21.89 times the 0.609. Remember, I don't want you to round even at this step. But I've already done this once, so I really just need one more 21.89 and then a half. So I'm going to multiply by 21.89 again, divide by 2, and I get 146. Like I said, or the other choice would have been to do store as x, and then you would have had that number also if you thought you were going to use it more than once. Plus 0.020 meters squared. You don't really need that second zero, but sometimes people leave it in there to remind themselves, no, I did round to the nearest thousandth. I didn't forget. Okay, last word problem. A scientist performed an experiment to study the effects of gravitational force on humans. In order for humans to experience twice the Earth's gravity, they were placed in a centrifuge 58 feet long and spun around at a rate of 15 revolutions per minute. So it circled all the way around 15 times every minute. I would get sick. Anyway, through how many radians did the people rotate each second? So we want radians per second, but we were given revolutions per minute. Honestly, this is just a test in your ability to use conversion factors, but something new and different. So I think maybe after this, you'll really understand the concept of a conversion factor. So I have revolutions per 1 minute. I want revolutions to go away. I don't want it in terms of revolutions. I want it in terms of radians. But I need to know the relationship between a radian and a revolution. Well, a revolution means once around. Well, what is once around in radian measure? 2 pi. So 2 pi is to 1 revolution, allows me to cancel the revolutions, and I get 60 pi radians per minute. But then I don't want minutes, I want seconds. So I'm going to put the minutes up here. I want the minutes to cancel, and I want it to be radians per second. I want second in there. So I just need a conversion factor. What's the relationship between minutes and seconds? There are 60 seconds in 1 minute. By the way, I just realized I made a little mistake. That's a 30 over there. 15, times 2 pi. Yeah, it's 30 pi, not 60. And so 30 pi times 1 over 60 is going to give me 30 pi over 60, or pi halves radians per second. So hopefully, maybe not yet, but hopefully you're starting to recognize pi halves as being 90 degrees, because pi would be all the way over here. So pi halves 90 degrees. So that means they are going 90 degrees every single second. It's pretty fast. All right, find the length of the arc through which the people rotated each second. So arc length, as soon as I see that, I write down my formula, and then I figure out my radius. Now, be careful, they said 58 feet long, but that's the entire length of it. So if the entire length is 58, then the radius would only be 29. And fortunately, I have this in theta now, like I have it in radians. So pi halves every second. And that comes out to be, again, I'm going to get rid of my pi now that I actually want to know the length of the arc. So 45.553 feet every single second. That's the length of the arc that they rotate through. Okay, we're going to finish up this lesson with a few extension questions. That means that they're a little bit harder. You're going to have to work a little harder at understanding how they fit together. So it says, use the graph to find the measure of theta, but I also see that it gives me arc length. So I'm going to write down my arc length formula. The problem with this formula is that measures the arc length given this theta. The theta goes with the actual arc that you're measuring, but I can't call them both theta. So let's just give this one a different Greek name. We'll call it alpha instead. There's lots of Greek letters. When you get into more complicated trig, we'll use alpha and lambda and theta and all kinds of things. So let's call this alpha. So 4 is the arc length, and the radius is also 4, and times alpha. So alpha is actually equal to 1. Now remember, we're in radian measure here. So in radian measure, 1 is approximately 60 degrees. Think about this. You're not used to seeing it without a pi. If this is 0 and this is pi halves and this is pi, remember pi is about 3.14. And then half of pi would be about 1.57. So if you hear a radian is 1, it's probably somewhere like that. That would be 1 because all the way up here would be 1.5. So radians, it's much easier to do radians with the pi still in it. But in this case, there's not. So we have to be accommodating. So now, what's the relationship between theta and alpha? So for any two angles that that form a straight line between 0 and 180, they would make two things that add up to 80, maybe 90 and 90, or maybe 30 and 150 would add up to 180, because 180 is always the straight line all the way across. For us, it's going to be alpha plus theta that make 180. Or in our case, because we're working in radian measure, alpha plus theta is equal to pi. So I learned that alpha is equal to 1, and I learned that pi plus theta is equal to pi, alpha plus theta is equal to pi. So I put those two together, solve the system of equations, and I get 1 plus theta is equal to pi. So theta is equal to pi minus 1. Pretty tricky problem. So if you didn't quite get it, that's okay. It's already a hard lesson. Using radian measure, given one positive angle and one negative angle that are coterminal with the angle shown. I guess that's just give. So I have 315, but they want us to use radian measure. So this is no problem. I can convert it. 315 is in degrees. So I multiply by pi, and I divide by 180. And that reduces to 7 pi over 4. So this is now 7 pi over 4. Now, when we did coterminals before, we only did them with degrees. We didn't do them with radians. This is a lot harder for kids, which is why it's in the extensions. But remember what we did before? If I hadn't done this in radian measure, I would just take 315 and I would add 360. And then I would take 315 and I would subtract 360. And you can do that and then convert them to radian measure. But if you convert first, or if you're just given something in radian measure, then you can add 2 pi, and you can add or subtract 2 pi, just like we did with 360. Of course, that's not going to help you because you need a common denominator, so I'm going to change it to 8/4. That's the same as 2 pi. And so one coterminal angle is 15 pi fourths. If I'm going to subtract 2 pi, again, I just need a common denominator. So 7 pi fourths minus 8 pi fourths is negative 1 pi fourth. Pi fourths, you may recall, is 45 degrees. So that makes sense. This is negative 45 degrees. So if you're given radian measure, add 2 pi and subtract 2 pi. Just like when you were given degree measure, you added 360 and subtracted 360. So this last one is a little tricky. There are 60 minutes in a degree of an arc and 60 seconds in a minute of an arc. I know that's super confusing. So back when degrees were first measured, remember there's 360 degrees in a circle. But what if you want to break down a degree even tinier? How do you make it even tinier? So somebody years and years and years ago decided that they would take 1 degree and they would break it down into 60 minutes. And then if they wanted to break it down even smaller, there are 60 seconds in one of those minutes. So here's how I do it. I just think to myself, a degree is like an hour. And then it's easy because there's 60 minutes in an hour and there's 60 seconds in a minute. So if you wanted to say 50 degrees, 30 minutes, 10 seconds, this would be the notation. Again, if I had made this up, I assure you, I would not have used feet and inches to suddenly mean minutes and seconds, but that's actually what these mean. That little symbol right there is going to mean minutes. This was not my choice. And then this is going to mean seconds. There are still places in the world, scientists, that actually use this, but a lot of people have converted to decimals. So today, if you were looking at something on a GPS, it probably would give it to you in decimal format. But even as recently as 10, 15 years ago, it still would have been in degrees, minutes, and seconds. And I still see things in degrees, minutes, and seconds. Actually, on somebody's tax map just this year, somebody showed me something and they're like, this is in degrees, minutes, seconds. Can you help me convert it? And so we did to decimals, which made more sense to them. So this is just more practice with the conversion factors. That is all this is. So this is 70.55 degrees. So I want it to be 70 degrees, but I need it to be something minutes and then something seconds. So how do I convert the 0.55 part to minutes? I use a conversion factor. In 1 degree, there are 60 minutes. So I multiply 0.55 times 60, and I get 33. So there are 33 minutes. I didn't get another decimal, so there's no seconds. 0.55 is exactly 33 minutes. So this concept of a conversion factor will really help you do a lot of different things. Now this one, I have to rewrite in 110 point. I have to change it to a decimal. So I do want you to start at the back end. It's the easiest way to do it. So I have 30 seconds. I'm going to write that in because I know it looks like inches. 30 seconds, and I want to convert it to minutes. So I say to myself, there is 1 minute is 60 seconds. That is a conversion factor that you know. So when I multiply that, I get 30 over 60, which is 0.5 minutes. So now you can think of this as 110 degrees and 45.5 minutes. And hopefully that makes sense. 30 seconds, half a minute. But now I want to convert my 45.5 minutes, which is just a single tick mark, 2 degrees. I want it to be in degrees. So I want to cancel the minutes, and I want to give it the degrees. So minutes is going to cancel, and I want it to be in degrees. So what's the relationship? 1 degree has 60 minutes. So I take my 45.5 and I divide it by 60. And, divide by 60. And I get 0.7583 repeating. And it says to the nearest hundredth. So I'm just going to do 110.76 because they asked for the nearest hundredth. And it still has degrees. And that would be my answer. So we won't do a ton of that in Algebra 2, but it kind of gives you a little taste of it to get you ready for pre-calculus, where we'll do a lot more of this. And honestly, just getting you to practice your conversion factors, which I think you use a lot of in science also. But that is it for section 9.2. Have a great day.